Hi everyone, this is Madhav. I'm going to walk you through this little circuit that you see here. You're going to need to know a little bit of basics about how AND gates work, how XOR gates work, to understand this half-adder circuit. So, for motivation, why are we learning about this particular circuit? Turns out it's very useful for adding binary digits. In particular, you might see here that we have some simple sums. If you have 0 and 1, you get 1, 0 and 0, you get 0. If you have 1 and 1, then you get binary 2, which is 1, 0. Notice here that not only are you getting the output, the sum is 0 for that particular unit, that particular digit, you also have a carry for the next bit over, the next digit over. In fact, I could say that all of these cases have a carry out of 0, whereas the sum is 1 and 0. So in fact, that's kind of what you see here. You are going to be building a circuit with two outputs. Of course, this might look like, how does this get to that? Let's work through it step by step. So we have to build a circuit. It's going to have a carry out and a sum as the outputs. It's going to have two input digits. I'll highlight this in green and this one in orange. It's going to have two input bits going into the circuit. It's a circuit that can add 2 bits. As a hint to the next video, this kind of thing will be useful when we're building larger circuits, because usually we're adding more than 1 bit. Anyways, to figure out, okay, we have the input and output set up. To figure out what goes on in the middle, we can set up a nice truth table. So I'm just going to fill this in over here. If we have a 0 and a 0, then the output sum is going to be a 0. Over here, it's going to be a 1. Over here, it's going to be a 1 again. And over here, as you saw at the start, we're going to have the sum equal to 0, and then we're going to carry over the bit to the next place, just like we had over here. In all other cases, the carryout will be 0, because you have at least 1 0, which means that the sum, it can still fit into the same bit. You don't need to carry it forward to the next bit. So now, based on this, you might recognize a pattern. If you're familiar with XOR gates, you might recognize that this is, in fact, an XOR as an output. Only if one of the inputs is a 1, you will get a 1. If you have both inputs as a 1, you will no longer get a 1. So what we can do is we can create an XOR gate to get the sum. So I'll just take X over here, Y over here. I'll bring X down, connect it to an XOR gate. And we've got our sum based on just this particular column of the truth table we've created. As for the other column, you might also recognize this pattern as a common gate. This is in fact an AND gate, because only when X and Y are both 1 do we output a 1. In all other cases, we output a 0. So here we can create an AND gate to get the output, Cout. Because I haven't given myself enough space here, I'm gonna draw this a little bit closer to the end. Here we are. So there's our XOR, and we're going to take our Y, feed it up there, feed this down here, and we have our half adder circuits. You'll see it's the same thing as what we had over here, just rotated. But you have the key insights. For the half adder circuit, you need an XOR gate to get the sum. You need a carry out bit that's created by an AND, and we figured that out using a truth table. Now, a half adder, as the half insinuates in the name, it's not fully sufficient to do addition of large binary numbers like we usually do in computers. In particular, notice this sum. So I'm adding 3 to 1, I get out 4, but notice what happens. 1 plus 1, I get a sum of 0, a carry in of 1. Then again, 1 plus 1, I get a sum of 0, carry out of 1. Now, I just called this a carry in, and I called this a carry out. Why is that? It's because if we look at this bit in particular, which is what you usually do when you're doing addition in computers, you just focus on one pair of bits at a time, one digit. You'll note that I have one carry input in just this one bit, and then I also have a carry output in just this one bit. So in fact, if we were to create a fully functional adder circuit, we need something like, I'll do this in purple, we'd need something like another input for our carry in. So in the next video, we're going to talk about how do we modify this circuit to deal with that extra input.